Hello everyone, my name is Seyed Mousavi. In this section of this course, I will demonstrate the use of particle swarm optimization for designing efficient three-dimensional antenna structure. The approach minimizes total length and bending cost to achieve smooth and optimized geometries. The project highlights the role of evolutionary computation in intelligent design and advanced engineering application. Section 5. Evolve antenna design by PSO algorithm. First, we cover some of the definition needed for the slide. What is antenna? Antenna is a device that transmits or receives electromagnetic waves by converting electrical signals into radio waves and vice versa. Evolved antenna is an antenna whose shape or geometry is automatically optimized using evolutionary algorithms instead of manual design. Optimization is the process of adjusting design variables to achieve the best possible performance under given constraints. Objective function here is a mathematical formula that measures how good or bad the antenna design is. Here, lower values means better performance, as we are dealing with cost function. PSO is a nature-inspired algorithm that simulates the collective behavior of birds or fish to find optimal solution. Also, for more information about PSO algorithm, please refer to section 1. Also, PSO has some elements like particle. Particle is a single candidate solution in PSO, representing one possible antenna geometry. Swarm here is a group of particles exploring the search space together, sharing information to find the best solution. Fitness or cost, which is cost here, is a numerical score computed by objective function that determines how good each antenna design is. Iteration, a full update cycle where particles adjust their positions and velocities based on personal and global bests. Global best or G-best is the best solution or the antenna design found by entire swarm up to the current iteration. Personal best or P-best is the best antenna design found by one specific particle so far. Inertial weight or W is a coefficient controlling how much of the previous velocity a particle keeps in the next iteration, which is a balance between exploration and exploitation. Cognitive component, or C1, is a PSO parameter that makes each particle move toward its own best known position. Social component, here known as C2, is a PSO parameter that makes each particle move toward the swarm's best known position. Velocity, the rate of change of a particle position, determines how fast and in which direction it moves through the search space. Search space, the multidimensional region containing all possible antenna designs that PSO explores. Convergence, the stage where all particles gradually move toward the same best solution. Bending penalty, a penalty term that discourages sharp bends or irregularities in the antenna's 3D path. Euclidean distance, the straight line distance between 2 points in the 3D space, used to measure antenna segment length. Now here we have an objective function, which is the most important part. It tells the PSO which antenna design is better. Shorter and smoother antennas get lower cost values and are considered better. It calculates the total length of the antenna by summing all distances between consecutive joints. Shorter antennas are better because they use less material. Also, objective function adds a penalty for sharp vertical bends by checking how much the z-coordinate changes between points. Smoother antennas get a lower penalty. So why this topic matters? Why antenna design in general matters? Because antennas directly control how efficiently wireless systems transmit and receive signals, affecting everything from communication range to power use. Why use metaheuristics like PSO? Traditional formula-based or manual design struggle with complex nonlinear 3D geometries, where analytical optimization is impossible. Why is PSO better in this manner? PSO efficiently search vast design space without requiring gradients, balancing exploration and exploitation to discover high-performance antenna shape automatically. Now we start the whole process of evolved antenna design by PSO algorithm from input, processing, objective function, and the output. The input here is going to be an antenna, which is represented as a series of 3D joints connected by straight segments. So an antenna is represented as a series of 3D connected joints by a straight segment. Like A is an antenna which has n number of joints, which is represented by P. So basically each P is a joint, but together is going to make A, which is an antenna. And each P has axes in X, Y, and Z in 3D space. So P denotes the 3D coordinates of the ith joint of the antenna. N is number of joint, for example 8 or any number. A representing the entire antenna geometry. So the full antenna is therefore a matrix of shape n plus 1 multiplied by 3. Each antenna design, one candidate solution, can be written as a flatted vector of A or X, which have multiple joints of P in X, Y, Z positions. So X, Y, Z 0 is P0, X, Y, Z 1 is P1, X, Y, Z n, which is Pn. This vector is what PSO is going to optimize. So the optimization problem is defined as minimum of fx for each x, where fx is the objective or cost function here, measuring how good the antenna geometry is. The antenna is evaluated according to two main criteria. Focal length, efficiency term. Shorter antennas are often more efficient and lighter, which is going to be calculated by the following equation as L, which we are looking for the Euclidean distance between consecutive joints. Also, the bending smoothness or penalty term. Antennas with sharp vertical bends, large jumps in Z axes are penalized, which is going to be calculated by the following equation as B. Thus, the final objective function becomes fx equal with L plus lambda B. And the lambda here is the weighting factor controlling the influence of the bending. So it is going to be a parameter, we can adjust it. We now minimize the fx function using PSO. Each particle P maintains a current position of xp, a velocity of vp, its best known position of p best, the swarm's best known position g best, which each iteration updates as the following equation, where W is the inertial weight balancing exploration versus exploitation, C1 and C2 learning coefficients, which are cognitive and social terms, R1 and R2 are random numbers in a range of 0 and 1. The process repeats for the defined number of iterations, like 200, and the global best solution gradually converges toward the most optimal antenna shape. Now output would be a simple result. After convergence, we obtain optimized antenna geometry, the 3D coordinates of A corresponding to the lowest cost found, and the convergence curve, which is the cost of fx over iteration showing the swarm's progress. Here in this image, we can see the result of a simulation. At top, we can see 4 antenna designs with 8 joints, which are optimized for the best performance by PSO algorithm. And below, we see corresponding convergence or cost over iteration by 200 iterations max. Now let's go to the Python environment for coding the same result we see in the slides. Okay, we are in the coding environment of Python under Spider, and we have 3 codes here. One of them is PSO on test functions. One of them is PSO on test function but in a 3D plot, and also the evolved antenna design problem, which is solved by PSO algorithm here. First, we start with the basic of PSO. So here we have the PSO algorithm, which is going to be tested on 8 different functions as before. with other algorithms which we solved, which are Sphere, Matthias, Rosenberg, Powell, Rastrogin, Ackley, Eggholder, and Bay, from 4 different categories, and they're going to be plotted in 2D, and also the 2D convergence also will be plotted also. So this is the main body of the PSO algorithm. Also, these are the required libraries. And we have the plot section. So basically, there is nothing specific about it here, just like the previous algorithms. The number of swarm size, which is the population size, is 50, and generation is 100. After running, we get some results here, which shows each test function how much time it is spent, or how much memory or RAM it uses, and also the final best cost value. So we have it for Sphere, for Matthias, for Rosenberg, and so on. And we have 2 plots, which it shows the best global best for each function with a red star. The more violet, the better situation. The violet area are the global best area, as we can see. PSO found for each 8 functions except Powell, because Powell is 4-dimensional. So it found it, but it's just not going to be presented in 2D dimensions. So for the Powell, we can see the result right here, which is 0. Also, we have the convergence for each test function solved by PSO. So as you can see, PSO solved very fast, and convergence happens very soon in the initial iterations. Also, we have the 3D plot for PSO here. We are going to run it. So I just consider for function here. We can see what Sphere function is look like really in a 3D space, and the best global best is found here as a red star. Also the Ackley in 3D form, and the best which is found on this test function, the Rosenberg, and also the Eggholder, which is one of the most complicated test functions for solving out there. So basically, any place on those violet area or purple areas are considered as the best solution found. Okay, here we have the main problem of a web antenna design. Here we are going to import our libraries. Also, I'm just gonna comment this section to produce a random population each time. Here we have our objective function section, which evaluates the cost of the 3D antenna shape based on the total length of the antenna and bending smoothness, which I explained in the slides. And so on. So basically, we have the first parameter, second parameter, and total of them. Here we are going to generate a random antenna with a given joint progressing upward in z-axis. Here we have the PSO parameters. We are going to consider 30 population as a swarm size in 200 iteration with 8 joints. And this is a dimension equation which I explained in the slides, which is going to be joints plus 1 multiplied by 3, because we have 3 dimensions. And here number of joints is so important. So basically, you will define the number of joints. So if I say 3, it's going to consider just 3, and it's going to be faster. But when you increase the number of joints, it's going to be more complicated, which we will see in the simulation ahead. Also here we have the PSO main body running. And at the end, we have the visualization of the antenna. Here we consider just 4 to fit the screen, and the convergence of each solution. So this is the result we get exactly as a slide. Each time it's going to produce a new candidate solution or antenna designs with 8 number of joints. Each one of them is antenna design. This is antenna design 1, 2, 3, 4, and corresponding convergence over iteration. So as you can see in the 3D space, there is a start, which is the red dot, and there is an end, which is a green dot, and each blue dot is going to be 1 joint. So we have 1, 2, 3, 4, 5, 6, 7, 8 with a start and end. So basically what you are seeing here for each antenna design shows the best 3D structure of an antenna which could transmit or receive signals. What that means in a simple term is that PSO identifies this 3D structure for the best antenna design or the 3D structure which improves transmitting and receiving wireless signals in the space for this specific antenna. So this shape by PSO's nature, considered the best. As you can see, convergence happened very soon in the 50th iteration, and a little bit of improvement in the 100th iteration, but it's going to be like plateau or flat toward the end. Or here. So the reason that we have different results each time is because each one of them is going to produce randomly and completely separately. Now we have 8 joints here. Let's consider just like 4 joints. See what happens. Okay, for 4 joints we have something like this. PSO is going to consider this form as the best shape for the antenna to transmit and receive signals. As you can see, some struggling happened with 4 joints by PSO. Let's increase the number to like 15. By 15 we get something like this. Now for the human eye it's going to be something weird, but actually this structure is going to perform way better than a lot of antennas out there, which is going to be designed by humans. So this shape is going to receive signals in the best perfect form possible. Now I'm going to show you that the increasing number of iteration is not going to affect so much. So I'm going to reduce this to 10 or maybe 6 and increase this to 500. We can see the convergence is almost the same. So with 6 we get something like this or this. So I don't know, 5. Even increasing the population is not going to affect so much. So here there's a problem. So basically PSO couldn't find anything. It happens, but it is very rare. If I run it again, it's most probably going to be fixed. So with 5 joints, we have something like that. Now I'm going to increase this to like 7, but I'm going to reduce this to 10 and this one to 300. This is very good performance, I can see here. Okay, this section and also the course is over here. I hope it was useful for you, and I wish you all the best.